All right. Okay, so welcome to the third plenary of COLT 2022. This plenary will be given by Professor Alon Orlitsky from University of California, San Diego. We hear a lot in our COLT community about information theoretic this, information theoretic that. Every once in a while, we don't know what that is. We just use the term because it sounds cool. A lot of times, though, information theory has been extremely important and key to many learning problems. Not least among these is anything dealing with sequences, anything dealing with prediction, logarithmic loss obviously enters in a big way. Alon Orlitsky has been at the forefront of these developments very early on. Some of his work was recognized by best paper awards from the Information Theory Society, including the work on compression of patterns in sequences with very large, possibly unknown size alphabets. Some of the work has dealt with prediction from individual sequences, worst case, stochastic uncertainty, etc. Alon has been recognized by the Information Theory Society with the 2021 Claude Shannon Award. He delivered his presentation, I guess, virtually, right, in 2021. Well, this year, we have the pleasure of having in-person talk by Alon about problems at the intersection of learning, computation, and information. He's an exciting and engaging speaker. So without further ado, I let Alon take the floor and tell us about robust learning from batches. Thanks.
Thank you, Max, and hello, everyone. So we're going to talk about, as Max said, robust learning from batches, and we'll see that the best things in life sometimes are almost free. And this is based on joint work with my students. Ayush Jain sits right there. So we're going to start. All right. Okay. So first, just a quick overview. We're going to describe some fundamental learning tasks and talk about data corruption, how we can address it via robust learning, and then we'll discuss this concept of learning from batches or from sources if you want, and we'll talk specifically about density estimation, and we'll discuss both discrete and continuous distributions, and then briefly we'll talk about classification, and we'll see that we can learn almost as well as if the data was just genuine. And this is based on 3 papers. And so mainly it's going to be an overview, and potentially we'll discuss a few proof elements. Right. Okay. So, so we live in the golden age of machine learning in the sense that many important applications are accurately learnable with modest resources, in the sense that we have within, a decent amount of data, not too much, and we can compute the algorithms on, short polynomial time. And these results build on a lot of work that was done by people in the theoretical machine learning community, including many present here. And typically they look at some, fundamental learning problems like hypothesis testing, density estimation, classification, regression, clustering, reinforcement learning, and hopefully soon enough also deep neural nets. Okay, so basically these are basic paradigms, and if you combine a few of them, you can get some pretty fancy results. Okay, and what these results often show is that as the amount of data increases, then you can perform better and better, and the error goes down, typically either to 0 or to the least that you can approach, and people make a serious effort to try to get as close as they can. You can see results like that. You get results that go to 0, let's say, and then people keep improving them a little bit, little, and so on. So there's a lot of effort made into getting the optimal results. And typically these are done via polynomial time algorithms, just so you can actually implement them, right? So, so I'm going to talk about mostly density estimation. And so, which I think should have been a second. Yeah, so I'm going to talk about here. So in this hierarchy, increasing hierarchy of or complexity of tasks, I'm going to talk about density estimation and a little less about classification. Right. Okay, so density estimation, you have a known distribution class. And there's an unknown distribution in this class that generates samples. And you want to estimate, based on the samples, you want to estimate the distribution. And the question is, what is the best estimate that you can come up with? Okay, and so we'll start with discrete distributions, and I'll be a little precise about this. So for a couple of reasons. Number one, I'm not sure. I know that some people know this material really well, but I want to make sure that everyone understands what we'll talk about. And also, we're going to take this definition and vary it in different ways. So I want to make sure that the basis we all get completely correct. Okay, so talking about discrete distributions, so the support set, a discrete support set without loss of generality, we can assume it's the element from 0 up to k minus 1, denoted by bracket k. And the set of distributions is the simplex, the collection of all distributions over these elements. And a distribution, as we know, distribution P consists of k probabilities, one for each element. So each of them is non-negative and they sum to 1. And we get samples from this distribution. And by samples, we mean a vector of S samples, x1 up to xs. Each of them is distributed according to P, and they're independent of each other. So the probability of a vector is just the product of the probabilities of the individual elements. Okay. Now, the distribution that we get is unknown, okay? And this distribution generates the samples independently, as we said. And based on the sample, we want to estimate the underlying distribution P. So for that, we need an estimator. And what an estimator is, an estimate QS just takes a sequence of samples, k to the s, and maps it to a distribution in the simplex. And when we apply it to the sample, that's going to be our estimate of this distribution P. So to see how well we approximate P, we need a distance measure. And the distance measure that I think many people in our community use, maybe the majority, and the one we use here is L1 distance, which is just the summation of PI minus QI. So PIs are the correct ones, QI are estimates, so just the sum of the absolute values, or equivalently, the total variation distance, which is just the sum not of the absolute value, but just sum of PI minus QI over just all the positive when they're positive. And because PI and QI sum to 1, this is just going to be half of the L1 distance. So these two are equivalent, and that's what we use. Okay, and then, so the distance of our estimator, so QS is our estimator, we apply it to the sample. The distance when observing the specific sample is just the distance between our estimate and P, and the distance, as we said, that we'll use is one of these two equivalent distances. And this value is a little too precise. It's our loss with a particular estimator for a particular sample and for a particular distribution. And we don't want to be so specific to what we observed. So what we want to do is find a fundamental concept about how well we do. So we want to see the fundamental difficulty of the estimation task. So what we want to do is actually eliminate the estimator, eliminate the sample, and eliminate the specific underlying distribution P, and that's what we're going to do in the next slide. So we're going to define what's called the mean max expected loss. You know, since we are here in England, this is probably like the queen of, you know, of VOSes. It's the first thing you'll try. So, so first we're going to remove the specific sample that we observed by looking at the expectation. So we'll define our loss of an estimator Q for distribution P to be the expected loss over all possible samples. So we eliminate, that way we eliminate the observed XS, the observation, and then we want to remove P by taking the worst distribution. So if we have an estimator, we'll consider the worst expected loss over all underlying distribution P. And then we also don't care about a specific estimator. So we're going to take the best one. Right? And so the loss that we'll define is going to be just the minimum of all estimator of the expected loss of this estimator for the worst distribution. And this is just going to be a function of the alphabet size, K, and the number of samples, S. Okay, so when we combine them together, it's the loss of the best estimator for the worst distribution in terms of the expected difference between them. Okay, so this is the expected loss of the best estimator for the worst distribution. Okay, and this is called the mean max expected loss. And the obvious question is, if I give you a distribution over K symbols and I give you S samples, how well can you do? Okay, so just go quickly over binary and large alphabets. So if we're going to look at the loss for alphabet 2 with S samples, and then we'll just mention what it is for alphabet of size K. So we're given S samples, and because K is 2, each one is Bernoulli P, and they're independent. Okay, and we want to estimate P. So the natural thing to do is to let N be the number of ones in our observation. So this number of 1 is distributed binomial with parameters P and S. Its expectation is S times P. Its standard deviation is square root of S, P times 1 minus P. And the natural estimator, given this sample, is the empirical estimate, which will just say the number of ones that we observe normalized by S. So its expectation is P, which is the correct value. And its standard deviation is square root of P times 1 minus P over S, because we're just normalizing this value by S. So we get that. Okay, and then the expected TV distance between, so our estimate of probability of 1 is N over S. For 0, it's 1 minus N over S. And the distance, the TV distance between that and P1 minus P is just the expected value of what we saw, N over S, our estimate minus P. And this is the mean absolute deviation. It's within a small constant from the standard deviation that we calculated here. So it's just some small constant times P, square root of P times 1 minus P over S. Okay, so that tells us that the loss for alphabet size 2 is order of 1 over square root of S, so it goes down with S. And then if the alphabet is of size K, then if you just want to get the order, then it's very easy. And if you want to get the exact constant, then that's something that we looked at some time ago. And it's this value here, square root of K minus 1 over 2 pi S, okay, roughly that. And again, we see that as the number of sample increases, the loss goes to 0, like 1 over square root of S, which is really good. And this is what we call the statistical limit. So the thing to remember from all of this is first the meaning of our definition, LKS, because we're going to modify it slightly in the next few slides, and then that it goes down like square root of K over S. Okay, right. All right. So this is statistical limit. There's nothing you can do. This is the best you can do. You cannot do any better. Okay. But so this is one example where you could say, okay, here we have a very simple calculation. We see the best you can do. It's nice. And of course, this is a very, very tiny part in the big paradise that we live in, where people identify, can learn a lot of things. However, in this beautiful paradise, there's a little bit of trouble. And it comes in the form of corrupt data. So when you talk about big data, then you get big problems. And the samples that you get, they come from all over the place, and they're often corrupt. And they could be corrupt because inadvertently there's some wrong measure, or there's like a faulty device that measures things, or you get some data and the data that you get is biased, or it's malicious, or it could be even adversarial. Someone is looking at the actual distribution, looking at other samples that you got, and then they modify the data that they give you to trick you. Okay, and in all these things, we assume that the identities of the corrupt samples is known. So you get a bunch of samples. It's not that you know these are correct, these are good samples, these are bad samples. You don't know which is correct, which is good, and which is bad. And the natural question is, can you still estimate the distribution P accurately? Okay. So, so this is a very natural question. So people have been looking at it for a long, long time. Started with Tukey and Huber in the 70s, and I think shortly thereafter Donohoe. Many books are written about it. Here are 5 robust statistics books. There are many more. There's been some revival recently in the machine learning, computer science literature, where people look for efficient estimation in high dimensions. And here again, 3 out of many more papers. Okay, and so the model, the common model that people use due to Uber is this: you have a parameter beta, which is less than half, and you assume that a fraction of at most beta of the samples are corrupt. And again, corrupt comes from a different distribution, could be bias, arbitrary, adversarial, anything. Okay, and the remaining fraction, 1 minus beta, of the samples are genuine, so they're distributed according to the correct distribution. And you can also generalize it to say that it's not exactly distributed according to P, but maybe something which is close to P. That's fine too. Okay, and typically, what people have done is looked at estimating distribution parameters. For example, we can show that if you take the median of S samples, then it will, and if your distribution is Gaussian, it will estimate the mean fairly well. So you can see here, the error will go down like 1 over square root of n. And I'm using this V for max. So it's going to be the maximum between 1 over square root of n and beta times sigma, where beta is the fraction of corrupt data that you have. Okay, and all of these assume that beta is less than half, because if beta is bigger than half, then you cannot know whether the samples you get are genuine. So the adversary can just give you some distribution. You think that's the distribution, you're estimating something completely different. Right. Okay. So, but there is a small secret that in this community of ours, and it's not secret like, like we'll hide it for you, but at least we won't thrust it upon you, okay? And that is that even as the number of samples goes to infinity, now that you have corrupt data, the error will not go down to 0. Okay, so in other words, there's a hard limit on the performance in the presence of corrupt data. Okay, so if you look at even the most basic problems like hypothesis testing, or slightly more complex density estimation or classification, if a fraction beta of the samples is corrupt, you will not be able to get to 0 error as you would hope to get. Okay, so what I want to show you why that's the case. Okay, so we'll discuss the source of all evil. Okay, so let's take this, and I'll show it to you for distribution estimation, but we could easily do it also for other things. Okay, so so suppose your alphabet is binary, the simplest, and you have a fraction beta of adversarial samples, and you want you want to learn the distribution from the samples. You remember that if the distribution was, if all the samples were fine, then you could learn it at a rate of 1 over square root of s. You could get to the right distribution. So, but here you have a fraction beta that are corrupt or adversarial. So we're going to even consider just 2 distributions. Bernoulli 1/2 minus beta over 2, namely the probability of 1 is 1/2 minus beta over 2. Probability of 0 is 1/2 plus beta over 2. And the complement Bernoulli of 1/2 plus beta over 2. Okay. So if the distribution is the first one, this distribution, Bernoulli 1/2 minus beta over 2, then the number of ones, so if you take S samples, the number of genuine samples is going to be S times 1 minus beta, right? Because that's the fraction, 1 minus beta is the fraction of genuine samples. So you get S times 1 minus beta genuine samples. And for each of them, you'll get one with probability 1/2 minus beta over 2. So it's going to be S times, and here we have what? We have 1/2 minus beta over 2, and then minus beta over 2 plus beta over 2. So it's just a little over S times 1/2 minus beta. Okay. So among the genuine samples, you get just a little over S, which is the sample size times 1/2 minus beta. And so what the adversary can do, remember the adversary can now modify any way they want. They can modify beta times S. So they can just, the remaining ones, they can just give you ones. So they'll force the number of ones that you see to be S over 2. So you'll see S over 2 zeros and S over 2 ones. And by symmetry, they can do the same if the distribution is Bernoulli 1/2 plus beta over 2. So what that means is that the adversary can force you to see a sample which consists of the same half zeros and half one, regardless of the distribution. Okay, so the same over samples for these two distributions. Now, and that means that because you see the same thing, you have to basically guess what the underlying distribution is. And if you look at these two distributions, the TV distance is just beta. And by the triangle inequality, no matter what you're going to estimate, it's going to be a distance at least beta over 2 from at least one of those. So no matter what you estimate, you may incur a loss of at least beta over 2. So what that shows is that while with genuine samples, the distance, the error goes down like 1 over square root of S. If you have a fraction beta, which are faulty, and this is, I'm modifying L to S to write L to S beta. It's the same definition that we went to min max, but just when you allow beta fraction to be faulty, that is we see is at least beta over 2, no matter how many samples you have. You can get a trillion samples, you will not be able to learn the distribution well. Okay. And this is for distribution estimation. This will propagate to any problem that you want, like classification and so on. You'll get the same hard lower bound. Okay, so the implication is that accuracy does not improve with the sample size S. And for example, if 20% of your samples are adversarial, then it doesn't matter how many samples you'll get, you'll still be off by at least 0.1 from a distribution, propagates to all learning problems. And the question is whether this is it, pack our bags, there's nothing we can do. We have to leave, even though like when we look at a lot of problems, people try to make marginal improvements, but once they have corrupt data, then already forget it. They're like 0.1 away. So all the small improvements they made, they're dwarfed by this value. Okay. So luckily, in some situations, there is hope, and that's what we're going to talk about today. So, I'm calling batches here because that's what they're called in the literature, but you can think of them as sources. I think that's, in my mind, maybe a better way to think about it. So in many applications, the samples are collected from multiple sources. So, and each source provides a bunch of samples or a batch of samples. Okay, so you can think about a sensor network. So you have a bunch of sensors. Each one provides you a lot of information. Or you can think about recommendation systems. People, evaluate movies or evaluate Amazon products. Each one provides a bunch of, or Uber drivers provide a bunch of, a batch of evaluations. Or natural language processing, you want to learn distributions of, let's say, language. You get some text, each book, each email, each paper provides you a whole bunch of data. Or crowdsourcing, you have people evaluating or performing different tasks. Each one performs things not just once, but gives you a lot of data by themselves. Or federated learning, you have phones providing information. Each phone provides you not just one sample, but a whole bunch of samples. So in all these things, you see that there are many sources. And the question is, can we use that fact to robustly learn the distribution? Okay, so let's define it a little more precisely. So what we assume is that you have a bunch of batches. So if you want, you can think of them as sources. And we assume that most sources are genuine, but some maybe not. For example, maybe in a sensor network, few of the sensors are faulty, or you get feedback from people, and some of them are giving you biased feedback, or you try to estimate the distribution for a particular author, but you get some texts that you think were written by that person, but in fact they were not. Or you have some malicious sources that falsify data, even they look at what other information you get, and then they falsify data. Okay, and this happens often. And in some applications, it happens for a significant fraction of the sources. So here are some examples. So according to like an article in CNN, 5% of Facebook accounts are fake. We also know it's not just according to them, it's also according to Elon Musk. He almost canceled the purchase of Twitter, maybe might still do it because he thinks there are more fake accounts than they claim. If you don't trust these two, then according to a Harvard paper, 20% of Yelp reviews are fake. And if you don't trust Harvard, you sure trust the local station, BBC. They reported that you can buy a fake Amazon review for £5. So if you look at things at Amazon, it costs £5 to get a fake review there. This is a company that does ad campaigns, internet web campaigns, and they say that 40% of ad campaigns actually use fraudulent clicks. So you get a company to do a campaign for you, but on the side, they'll make sure that they get the result you want to get. And we know also in finance, it's known that the analysis is also only as good as your data. Okay. So this was modeled by Xiao and Valiant in 2017. And it said, okay, it's pretty much what we had before. Your alphabet size is K, you have M batches or M sources, you have N. Each of them is of size N, could be more than N, but let's say at least N. And the good batches are IID samples from the underlying distribution P. And again, this can be relaxed, can be doesn't have to be exactly P, but the remaining remaining batches, remaining sources are arbitrary, may depend on P, even on good batches. And the only thing is that there's a parameter beta, which upper bounds the fraction of adversarial batches. Okay? So of these M batches, at most M times beta are bad, the remaining M times 1 times beta are genuine. And the question is, how well can you learn a distribution of alphabet size K with now we have slightly, again, different parameters. We have M batches, each batch is of size N, and beta is the fraction of batches that are faulty. Okay. Right. So as often happens, actually let's first see why batches can help. So let's look at, again, a simple example. Suppose, again, binary alphabet, like we looked at before, K is equal to 2. And suppose we even have just 3 batches, okay? And suppose that beta is 1/3, means 1/3, in this case, 1 batch can be faulty, but 2 batches must be genuine, distributed according to P, and 1 batch can be anything, okay? So as the batch size, remember that for the general, the general problem of corruption, as the number of sample increases, you'll still have a strict lower bound of beta over 2. Here we'll see that that's not the case. So as the batch size N goes to infinity, then each genuine batch will converge to P, right? You have Bernoulli P, each of those, the fraction will converge to P, roughly like 1/square root of N. So all you need to do is find a distribution Q, which is within this 1/square root of N from 2 of the 3 batches. Okay, and 1 will exist because, for example, the actual distribution P is going to be within 1/square root of N from each of those 2 batches. And so this Q that you'll find is going to be within 1/square root of N from P. So you have 3, one of them, the adversary can do whatever they want, but in the 2 that are correct, they're both going to be roughly P. So you're going to just say this is my P, and you can see that you can learn to a distance 1/square root of N. So this is the basic thing that why batches can help. Okay. As happens often, this problem actually in a different disguise has been looked at many years ago by Dono and Liu. And they looked at a more general framework that they looked at in the context of what they called minimum distance functionals. So they said, okay, you have a collection of a parametric distribution family, F theta, for some parameter theta, could be like we looked at some real number, or it could be a vector. Okay, and you get S samples, and a fraction 1/1 beta of them are going to distribute it according to the real F theta for some theta in this class, and the rest are adversarial. And what you want to do is you want to estimate this parameter to some distance measure d. Could be, this is general at this point, okay? And they found a general low bound. They said that for any s and beta, the best that you can do in terms of this distance, okay, is at least half the maximum distance between theta and theta prime in your collection, such that the TV distance between f theta and f theta prime is less than or equal to beta. This should look to you very, very similar to what we did for the binary example, because what it says here is that if you have two distribution f theta and f theta prime whose TV distance is less than beta, then the adversary can fake them. So if you have two distributions that the TV distance between them is small, then just like in the case of the binary case, the adversary can make them look the same. And in that case, the loss that you'll have is d of theta and theta prime. And so, as we said, the best you can do is half of that by the triangle inequality. Okay, so they looked at a more general example of the very simple binary example that we looked at a few slides ago. Okay, and this, if you just think about a little bit, this is actually the same problem as the batches problem, even though it turns out that Xiao and Valiant may not have seen this, but it's the same. So for the batch problem, so you can view each batch as distributed. So you have an underlying distribution P, which is not necessarily binary. So, and then take n samples. So the distribution, all you care about is how many times each value appeared. So essentially you can look at each batch as distributed multinomially with parameter P and n samples, okay? N is the batch size. And so this is exactly the Dono and Liu formulation, okay? And then again, even though they didn't realize it, but essentially they've used the same technique, and they applied it to this collection of distributions. And what they showed that for every k, m, and n, beta less than half, if you evaluate this, you'll see that the best you can do is at least beta. That's the fraction of faulty batches divided by 2 times square root of 2n. So that's, well, it's a low bound, but as a low bound, it's a good low bound in the sense that at least it goes down, so you don't get its constant. So it shows that, okay, maybe you can do something that goes like 1 over square root of n. Okay, and this is, again, notice that it's very similar to the binary example for a couple of reasons. Number one, we see that there's no alphabet size does not appear here because it actually doesn't matter. If you have two distributions, you can just imagine that they're binary. So the alphabet size will not enter here, number one. And number two, you see that the number of batches also does not matter, and that's equivalent to, because the number of batches are the number of samples that you get. And that's the same as what we had before with the binary example. It doesn't matter how many samples you get, the lower bound was the same. So here, the number of batches corresponds to the number of different samples from this multi-million distribution you get. Okay, so this looks, when you look at it, this looks very similar to the binary example that we looked at, okay? And we'll call this, we had the statistical low bound, we call this the adversarial low bound. So this also gives you a low bound on how well you can do, okay? Now for upper bound, what they derived the algorithm that for beta, the corruption ratio less than 1 over 900 achieves something. So we have achieves at most beta over square root of n. And this again is the max between that and k plus n over mn. So just a couple of observation. This part meets the, and this is some constant here, and meets the low bound, the adversarial low bound. And this part almost meets the statistical low bound. If you remember, the statistical low bound was square root of k divided by the number of samples, s. The number of samples is m times n, m batches, each of size n. So you get square root of k divided by the number of samples, except it's a little weaker because you add they add n here, and if your samples are, if your batches are large, so this will not meet the lower bound. But an even bigger problem is that their algorithm runs in time which is exponential in k, and therefore they cannot actually calculate or simulate or do things. Because k, the alphabet size that people look at most common today, if you look at natural language processing, k is 500,000 words, so this k could be quite large. Okay. Now, and what in 2019 we found a polynomial time estimator with near optimal complexity, and at the same time, Chen, Li, and Moitra found a quasi-polynomial time algorithm with a quasi polynomial sample complexity as well. Right. Okay. So, so let me tell you what the results that we get are. So remember that we have the statistical lower bound, which is square root of k over mn. Mn is the number of samples s. Okay, and we have the adversarial lower bound, which is beta divided by square root of n. Okay, so clearly the maximum of the two is the lower bound. Okay, and the estimator that we have runs in polynomial time, and for all beta which is less than 0.49, essentially less than half, okay, and all alphabet size, batch size, and number of batches, it achieves something which is at most beta divided by square root of n, this quantity here, the low bound, the adversarial low bound, times log of 1 over beta, and the maximum between that and the statistical low bound. Okay, so a couple of observations. Number one, works for beta not just less than 1 over 900, which is like saying that only 1 out of 900 batches are faulty. Here, the number of faulty batches could be half, essentially. Okay, and it achieves both lower bounds, both the statistical and adversarial lower bound up to a constant factor. This is the big O here. With the adversarial lower bound has a small log 1 over beta factor. Now, you might think that maybe beta is 20%. I think I have this calculation later on. This is not a very large factor. And it also observed that there's no trade-off. It's not like the sum of these two, it's just the maximum. And the fact that it's the maximum and not the sum, it will tell us, as we'll see, that actually you can do things almost as well as if the samples were genuine. We'll see that, I think, in the next slide. Okay, it runs in polynomial times, and because it runs polynomial times, it's the first that you can implement in those social simulations. Also, you show you simulations for the next problem, which is continuous distributions. Right. Okay. So this tells us that robustness you can achieve almost free. Let's see why. So remember, k is the alphabet size, n is the batch size, or the number of samples you get from each batch or from source. M is the number of batches or number of sources, and beta is the fraction of sources or batches that are corrupt. And what we see is that the best that you can learn a distribution is at least clearly the maximum of the adversarial and statistical lower bound, and at most essentially the same, essentially the maximum. Okay, so so the statistical lower bound, this part, square root of k over mn, true even if all the samples were genuine. So this is no different. Okay, and the adversarial lower bound. So remember, if we got the samples individually, that was our first example, then we saw that the best you can do is beta over 2. It's a hard limit. But now we see that with batches, it goes like beta over square root of n. Okay, and so now let's see what happens. So if you have some error in mind that you want to achieve. If your desired error is below the adversarial lower bound, you cannot achieve it, right? So this is the adversarial lower bound. If your desired error is less than that, then clearly you cannot achieve it. There's a lower bound. But if it's slightly above the lower bound, and what we mean is there's this additional factor of log of 1 over beta, then you can achieve the statistical lower bound. So, and why is that? Because if you you're trying to get to learn the distribution to a certain accuracy. If you're trying to learn it to below beta over square root of n, then there's nothing you can do. You cannot do it. But if you try to learn it to above beta over square root of n, or more specifically above beta over square root of n times log of 1 over beta, and I'll do the calculation to see how much worse it is in the next couple lines. But if you're trying to do above this value, then you can achieve this bound, and you only depend on whether your value that you're trying to achieve is above this lower bound or below. If it's below this statistical lower bound, you couldn't do it before, and you will not be able to do it now. But if it's above this statistical lower bound, then if you could do it before, you could do it now. So in other words, if it's below this beta over square root of n, yeah, you cannot do anything. But if it's above, if the accuracy that you are trying to get is above this beta over square root of n, then you can achieve it because it's max, not summation. You can achieve it with the same number of samples as if all the samples were genuine. That's what we call robustness is almost free. So just to see how much this extra log of 1 over beta is, so let's do an example. Suppose we have 10% corrupt batches or sources. N is 1,000, each source is 1,000 samples. Then beta times this value, beta times square root of log of 1 over beta divided by square root of n is going to be roughly 0.5%. So, and these are maybe reasonable numbers, one might think. So if you are trying to learn distribution to less than 0.5%, to distance less than 0.5%, no, you cannot do it. But if you want to learn it to more than 0.5%, then you need as many samples as when all the samples were genuine. Now, true, there's a constant here, so I'm ignoring that constant, but ignoring that constant, what I said is true. And that's why we say robustness is almost true. We good? Yes. Yeah, this beta could be anything. Oh, okay. So you could change, it needs to be less than half. And for these calculations that we have for other things not to explode, you need to be strictly less than 0.5. So we're just giving you 0.49. But you know, like there's a trade-off. So if you the closer you make it to 0.5, there'll be other things that will go up. So yes.
Better known, and does it help to know it?
That's a very good question. So when we wrote this, so the question is whether beta is known, right? That is a really good question, and it bothers us for a long time. And when we wrote this paper, we did not know. But about, I don't know, maybe a year ago, or half a year ago, we realized that actually there's a very nice way to address this. And we actually posted, if I skip this, will it be difficult to get back? So we posted, because I think I have it, okay, I'll show you later. We posted, we wrote a paper, which is actually I like a lot. It's a small paper. It says like, we're thinking of like a tile, you know, like the, what's the Apple device called? Air tile, right? So you have a device that, we related it to the following problem, that you have you have a tile, like a device that you can find a location, but imagine that you need to specify like a distance that you want to, if you specify a distance that if you're within that distance, it will, you specify, let's say 1 kilometer, okay? And that you want to find it to within like some distance, and there's the accuracy that you'll get will be related to the distance that you want to that you allow. And the question is, you want to achieve the best accuracy as if you knew the distance in advance. And in fact, you can do it. And it's a paper on archive. If you look at it, if you want, you can search for it. It says something like robust algorithms don't need to know the corruption parameter. And we still like the paper a lot, but unfortunately, Max's co-conspirator, the other technical chair, Pauline Lowe, I think a day after this thing was published, she sent us an email saying she really likes it, but she realized that the technique that we thought we came up with is called Lepsky's method. So at least that part, so if you look at Lepsky's method, that will show you that actually you do not need to know the parameter. We didn't realize it, we wrote the paper, I still like the paper, but the application to this is maybe new, but the technology behind it is called Lepsky's method. So you don't need to know the parameter. Okay, we don't know, and I think that Ayush will be in a better position to tell you, but what I can tell you is that this log factor is also like for people who look at Gaussian distribution, they have the same log factor they have it for adversarial sources, and they think that it's inherent. So we don't know. But that's another very good question. No, you'll just get so if there's a function beta 0 that is corrupt, if let's say, so here you'll come up with an upper bound. You set most 40% are corrupt and you'll get some value. But let's say the value, the corrupt fraction is not 40%, but is like maybe 30% or something, you'll get a value that corresponds to that. We're good? Okay, so so here are some experiments. So you have a random distribution P, and looked at different adversarial distributions with varied TV distance from P, from the underlying distribution. And we're going to show results for the worst adversary amongst those that we experimented with, or Ayush experimented with. And we're going to compare the algorithm's performance to two estimators. Okay, one is the naive empirical estimator, so the one that does not utilize the batch structure. Okay, so what it does is just estimates P as the empirical distribution of all the samples. So it just takes all the samples, combine all the batches, combines together, and finds the empirical distribution. Okay, and because it ignores the batch structure, then from what we saw from the coin, we know that it might incur a loss, which is for some distributions might incur a loss, which is at least beta over 2. So this is comparison to a bad estimator. Then we'll compare it to an estimator which is really good. It's an oracle, so it actually knows the adversarial batches, it knows the good batches, and then what it will do is we'll just estimate the empirical distribution on the good batches. Okay, and this is it's not affected by the adversarial batches, and because of that it will achieve the statistical lower bound, which is square root of k divided by the number of good samples, which is mn times 1 minus beta. Okay. So here are the results. So let's see how we're doing in terms of time. Not well. Okay, so so basically what you can see here is that the blue line is the empirical estimator. Okay, and the red line is the oracle, and the green line is our estimator. And you can see essentially in all cases our algorithm essentially achieves the performance of the oracle that knows which batches are good and which batches are bad. Maybe this one is a little interesting because we know that we have the adversarial lower bound is beta divided by square root of n, and that adversarial lower bound only applies to us. It does not apply to the oracle, because the oracle knows which batches are good. So you can see the beginning here in this plot, n changes. So at the beginning, we have a higher adversarial lower bound, 1 over square root of n. So it takes a little bit of time, or n has to be at a certain size before you approach the performance of the oracle. We're good? All right. Maybe let me skip the algorithm right now, and then if you want, we can come back. Let's see if we can come back to this at the end if people are interested. Okay, so okay, I want to next talk about continuous distributions. So far we talked about discrete distributions. Now I want to talk about continuous ones. So so with continuous distributions, we know that even if you get all genuine samples, you cannot learn a distribution, because imagine that you have continuous distribution, you'll not see any repetitions, and you don't know if the distribution is continuous, so you have a bunch of spikes in these locations that you saw, so there's just no way to learn them. So when you want to learn continuous distribution, you always need to tell a story, like how you're doing it, what exactly you're assuming. So, so one alternative that's become fairly popular in recent years is that you don't restrict the collection of distribution you learn. You still want to learn any continuous distribution, not necessarily parametric, any continuous distribution, even continuous mixed distribution, discrete distribution, anything. But the only thing that you say is you want to learn it as well as a piecewise polynomial. Okay? So just to be, so here is a little more description. So you have a T-piece degree distribution is a distribution that consists of T pieces, and each is a degree D polynomial. Okay, so like for example, here we have 4 pieces, and each is a degree 3 polynomial. So that's a 4-piece degree 3 distribution. Okay, and we let PTD be the collection of all such distributions with T pieces and degree D. Okay, so for example, PT0 is the collection of all histogram with T, all flat, flat pieces, all with T histograms. So it's collection of all histogram with T pieces. PT1 is the collection of all piecewise linear distributions. Okay, and what we want to do is we want to approximate and the nice thing about this collection, and one reason why people are looking at it, is because you can approximate any piecewise continuous distribution with not necessarily polynomial. If you take any distribution that's piecewise continuous, you can approximate it with sufficiently large T and D by polynomials. So here is just an example. So for example, here, if you take a Gaussian distribution, and you can see that you can approximate it really well by a 4-piece degree 3 distribution. Okay, and many staple distributions like Gaussian mixtures, and so on, you can approximate with very low T and D. So low concave, unimodal, bimodal, and so on. You can approximate really well by this distribution with small T and D. Okay, so so if you want to learn from, again, genuine sample, the precursor to what we're trying to do, so define distance D of P, PTD is the collection of all T piecewise degree D distributions. And the distance between a distribution P and PTD, note like this, is the smallest TV distance between P and any distribution in this collection. Okay, so maybe I can skip things a little or go a little fast. So what a bunch of people showed was that the best that you can actually learn a distribution to alpha times for alpha, which is roughly 3. You can learn any distribution to, let's say, 3 times the smallest distance plus something that goes down with the sample size, like 1 over square root of S, the same as before. And they also established a lower bound that no matter what you do, you'll be at least twice the distance of the closest piecewise polynomial plus essentially the same quantity here. Okay, and notice that T times D plus 1 here represents the number of parameters, which is K. So that just takes the place of K, right? And then Acharya, Diakonikolas, Lee, and Schmidt found an efficient algorithm for that achieves 3, and kind of happy because Jadev came from our group. And then we actually improved this constant alpha from 3 to 2 and 2 plus epsilon, and which is optimal. That's recent, but not, yeah. But this is for genuine samples. Okay. So now for learning, for robust learning of piecewise polynomial distributions, then there's the statistical lower bound, which is twice the distance from the closest polynomial, plus this statistical error. And there is also the adversarial lower bound, which is, again, very similar to what we had before. This twice the distance from the closest polynomial, plus at least beta of square root of n, just like before. And what you can do is you can essentially, you can show that you can actually achieve both. You can achieve some alpha, which alpha is going to be, again, roughly 3, plus the maximum of these two. There's the same log of 1, square root of log of 1 over beta here, plus here there's O tilde. So here there's a log n coming up, which is not as good as what we had before. Okay, so it's the first robust estimation algorithm for continuous distributions from batches, achieves the adversarial batch up to a small log 1 over beta, and achieves the statistical low bound up to logarithmic factors if in n over beta. And again, same shows that robustness is almost free if what you want to achieve is above this value, the lower bound essentially. Then you can do it with essentially the same as you did before, except now there's this extra polylog factor, runs in polynomial times and allows for the first simulation. So I'll just show you the simulations. Okay, actually, so there's also, I should say, there's related work by Chenley and Moitras. They did not look at continuous distribution, but they looked at structured discrete distributions related to this problem. So they had some very nice results. I should just mention that. And here are the experiments. So we compare to the same two estimators, naive empirical estimator that does not utilize the batch structure, and Oracle that knows the identity of the good batches and uses them alone. And look at, in this particular experiment, I'll show you the fraction of corrupt batches is 40%, and N, the size of each batch is 500. So we just want to get numbers that are reasonable, not huge. And M times 1 was beta, that's the number of good batches, again, 62, a reasonable number. So here are the experiments. So, so the underlying distribution here is a mixture of two Gaussians. All the Gaussians will have variance 1. So it's a mixture of a Gaussian with mean -2 and another Gaussian with mean 1. You can see them here. So the black line is the actual density. It's a mixture of these two Gaussians. And the adversarial distribution that adds the noise with 40% is normal 0, 1. Okay. So what you see here is if you want to approximate using piecewise linear polynomials, so just linear polynomials, the black line is the underlying distribution. The empirical estimator just looks at this mixture of these three distributions will give you the red line. It's completely off. The blue dots is the Oracle that only uses the correct samples, the batches that come from this distribution. You can see them here, and you can see that our algorithm performs almost as well. And here is when you move from piecewise linear to piecewise degree 2 polynomials. Again, this is the empirical here, and the green and the blue are the Oracle and our estimator. So almost the same. Now there's a third part, and I think I'm out of time a little bit. Yeah. So you can do essentially the same for classification, and classification will not be able to achieve 0 error. But you can look at the axis, the additional error compared to the best classifier, and you can get essentially the same. So it's, again, you'll get whatever the statistical and adversarial lower bound give you. Okay, right. So just to summarize, we looked at robust learning where some samples are corrupt, and specifically a fraction beta of the samples are corrupt. And we said that it gives you a hard limit on the accuracy for any number of samples. And then we considered robust learning from batches or from sources, and where fraction beta of the sources are corrupt. And this arises in many applications like sensor networks, recommendation systems, natural language processing, and so on. Now, again, the beta fractions of the sources are corrupt and can be even adversarial. And we derive the first, in the context of robust learning from batches, we could derive the first computationally efficient algorithm that It's also essentially optimal. Simulation, therefore, because it's computationally efficient, to first simulation for discrete distributions, the results, I think, are decent. The first estimators for continuous distributions, again, they're near optimal and efficient for this class PTD of piecewise polynomial, and classification, again, near optimal and efficient for interval classification. I didn't get to talk about that. Okay, and shows you that the best things in life are almost free, namely up to the adversarial lower bound, we can achieve the same accuracy as for genuine samples.
Are there questions? If it's questions upstairs, okay. Just can you just repeat or rephrase the question?
Yeah. So I can say it will take about 10 minutes, so I can go in great detail. Or I can just say in a few words, but if you want, sorry. And he's asking about asking for some details about the proof. Basically, as you could see, if the distribution is binary, it's fairly easy to do it, right? I mean, like the concept is we said just find two distributions that are close to each other, and that's it. The difficulty comes when the alphabet size increases, and then you do and like I said, in many applications, the alphabet size is very low. Language processing and so on. So the problem there is you're trying to find a direction in which you have a distribution of the case, and you're looking at the TV distance between two distributions. The TV distance between two distributions is you're trying to find a subset of the symbols over which one distribution is large and the other one is small. If you take the supremum over all subsets of the difference, that is going to be the TV distance. So the trick is to find a way to find a subset of the elements over which this distance is large. So what you can do is you can express it as an inner product of your distribution with a 0-1 vector, where the one will collect the locations for which one distribution is large, the other distribution is small, and the trick is to find this vector that will maximize this. And you're trying to find a direction such that the batches or the sources that are corrupt will give you a high value, and the sources that are not corrupt will give you a low value. And the way you do it is by estimating the variance in two different ways, in such a way that so that you find two expressions for the variance, two expressions for the variance that you can find empirically, and this is what you use as your proxy, and you try to find this way this direction of the vector that will separate the good batches from the bad batches. Once you do it in this direction, you'll have many more batches. So you throw the batches that are high in this respect, and you can show that you're eliminating more bad batches than good batches, and you iterate. That's the rough idea. But if you want, I can show you more.
Hi, thanks for a great talk. I really like these results. One quick question is, I think in Valiant and Chow model, they also looked at beta larger than half, in which case they tried to do this kind of list decoding version. So I was wondering if you can do your results also have a version where you can just give this several sort of candidates, one of which will be
right. Okay. So first of all, that's correct. So if beta is larger than half, the way I said it, you will not know, you will not be able to tell what is the correct distribution, because the eavesdropper can just make it whatever they want. Not the eavesdropper, sorry, the adversary can make it whatever they want. And what they do is they say, okay, what we can we can, in that case, break it into a collection of possibilities. So we'll give you for this cluster, we'll give you one possibility, another possibility, and a third possibility. And this is the possible values. And then once you do that, it's sufficient to get a few genuine samples that you trust, and then you can estimate the distribution. Now, this is where I need to call on Ayush. Okay, is that something we can do?
Yes, so it's possible to extend these results for the list decodable setting. So basically for that, what we need to do is we need to combine the techniques used in our paper and the techniques used for list decodable setting for Gaussian mean estimation. And a combination of those two techniques will work.
Thanks.
I think in the interest of time, we're gonna end the session now, but like Alon is here and may answer some of your questions, and we should thank the speaker again. Thank you.